Hi all. So today we are going to see what is heap tree. Okay, before learning, we are in the unit of trees. Okay, I hope you remember this. And trees is a non-linear data structure. Okay, so where you won't have a linear fashion of arrangement, you'll be having here and there arrangement of data. Okay, so then in trees, we saw some terminologies of trees. Then we saw what is binary trees, right? So binary tree is okay, so first we saw what is binary tree. Binary tree, it has at most two children. Okay, at most two children. Okay, so next, so the binary tree will have at most two children. So that is, it can have either one child, okay, two child, or zero child. Tree can have, node can have no child also, but it must have at most two children. Okay, so next type of tree we saw is binary search tree. Okay, so what is binary search tree? Binary search tree will have at most two children, but the main property of binary search tree is the left side tree will have lesser values than the root node, and right side tree will have greater values than the root node. Okay, so that is, this is left and this is right. Okay, so this is the main property of binary search tree. So when you're constructing binary search tree, you should construct in such a way that your left side tree will be lesser values, must have lesser values than the root node. Okay, in construction of binary search tree, we also saw some traversal methodologies, right? Okay, so in traversal. So why we need traversal? Since it's a binary search tree, so this tree is constructed, or the main purpose of this binary search tree is to do searching operation. So in searching, you have to do traversal. Traversal is moving from one node to another node. In array also we did traversal, but it is very easy because the data are arranged in continuous fashion. So our traversal was very easy. So we are not pinpointing. We did pinpoint more concept of traversal in a linear data structure. But in binary search tree, since the data are arranged in non-linear fashion, traversal is a main topic, main concept. Okay, so this binary search tree is a one of the tree used for searching a data in binary trees. Okay, when the data are arranged in non-linear fashion. Since it is doing this the searching purpose, we need to learn about traversal. Okay, how they are traveling, in what way they are traveling to find a node from the tree. So to do the traversal, there are four different types of traversal in binary search tree. Okay, one is in order. Okay, where in order means left data and right. Okay, next is pre-order, where data left and right. Last is post order, left, right, data. Okay, and finally it is level order. So level wise we will be keep on searching the data. Okay, level wise. Fine. So here the data is by changing the position of data, we are traversing. Okay. So first, if the data is present in the middle, it is in order. If it is data present in the first, then it is pre-order. If the data is present at the last, it's the post order, and level wise traversal is level order. Okay. So these things we saw in binary search tree. The third type of tree we saw was AVL tree. So AVL tree, it has a property of binary search tree plus balancing factor. Okay, okay, balancing factor. So the balancing factor can be -1, 0, and 1. Okay, so whenever you're constructing a tree by using AVL method, then you have to find the or satisfy the property of left smaller than root and right greater than root. Plus, you have to follow you have to use this balancing factor along with it. Why we are going for AVL tree? Because when you're constructing this binary search tree, for example, if 10 is the root node, then left side tree should always have lesser values. For example, 7. Okay, and right side tree must be bigger than 10. Okay, for example, 13. And whatever nodes coming after the 7 should be lesser than 7 and lesser than 10 also. So, for example, 6. Okay, 6 and 8. Okay, so see this left side tree, 6 is lesser than 7, 8 is greater than 7, but this 8 is not greater than 10. Similarly, it can be 11 and 12. Okay, so 11 is lesser than 13, but it is not greater than 10. So, but it is greater than 10. So, it is in right subtree, but it is lesser than 13. So, it is in left of right subtree. So, likewise, you have to construct a tree. For example, if I'm giving one more data called 5, where it will be by the property of binary search tree, it will be fixed here. 4, again by the property of binary search tree, it will be put here. If it is 3, another data is 3, I'll put here. And again 2, here. So if I keep on including the smaller values, it will be bombarded or it will be filled in left subtree only. It's not bombarded, it's just filled in only left subtree of this root node. Okay, so it will be keep on increasing. So left subtree will be keep on increasing. So in order to avoid this, okay, so why if it is keep on increasing, there is no problem, but the memory space is wastage. But here there are many spaces, but this is wasted. Okay, one more thing, if I want to search one node at this position, I have to travel a long way to find this node, right? But here there are only it's lesser than 10 nodes, so you will do the traversal. But if it is more than 10,000 nodes are there, if it is elongating, okay, sorry, if it is elongating a long time, okay, for a very lengthier version or lengthier, okay, for a very long direction, okay, so what happens? You cannot find a node, or finding a node take a large amount of time. The time for complexities will be more. Okay, so because of that, we are going using balancing factor to reduce the balance to make balance the tree in not in one side, but to exactly balance the entire tree. So in order to do that, we are going for this balancing factor concept, and whenever the tree is not in balanced way, then you will be doing either LL rotation, RR rotation, LR rotation, and RL rotation. So when the balance is violated, when the balance of a tree is violated, then you do some kind of rotation and make the tree as proper balanced one. Okay, so this is the property of AVL tree. So today's concept is about, okay, heap tree. Okay, so what is heap tree? Heap tree is a binary tree. Okay, so here in heap tree, you have to follow two rules same way. One is it should be complete binary tree. What is complete binary tree? Okay, plus it can be either max heap or min heap. Okay, I'll teach you each and everything. Okay, so first, what is complete binary tree? So what the complete it's a binary tree, so it must have at most two children. Sorry, two children. Okay, at most. So at most is the keyword. So it can have either zero child, one or two, not more than two. That is what this meaning is. Okay. Since it's a binary tree, it can have at most two children. Okay. What is complete binary tree? So complete binary tree means it can have at most two children, but it should be in a complete way. That is, it should be left as possible. Okay, what is left as possible? For example, if the tree is given in your hand, for example, 5, 7, 3, 1, 5. Okay, it is 6. I don't want to confuse with the duplicate datas. 9 and 10. Okay, these are the datas given. Please forget the complete binary search tree concept. Now remember this alone. Okay, in binary search tree we'll be filling left with small and right with greater, and A will be same way, but if the balancing factor is affected, you'll rotate the tree. Forget that. Now heap tree, it should be complete binary tree. What is complete binary tree? It should be left as possible. 7, 3. Always the left node should be filled, then followed by right node. Again, 5 is inserted, 7 is inserted, 3 is inserted. Next is 1, left as possible. 6, here. 9, 10. Don't think about lesser value left side, greater value right side. Don't think about that. It should will in such a way that you should always start from left and fill the tree. Okay, you must fill the tree in as left as possible. Okay, so that is what complete binary tree, left as possible. Okay, so heap tree follows this property along with this max heap or min heap. What is max heap? For example, so see here the same concept, same example I'll take for creating max heap. Okay, so how to create it? Okay, the 573169 are the data. How to create max heap? Okay, max heap. Okay, by the word you can say you should have maximum or larger data as root node. Okay, node. Okay, so for example, 5 is the first node. Okay, next 7 is the next node. So left as possible. But here, if it is max heap, the root node or the parent node must have, okay, or parent node, think like that. Okay, okay, root node. Okay, so if 7 is the next data to be inserted, first insert the data as left as possible. Then check with the root node. Check with this parent. Okay, okay, so its parent is 5. So check whether it is larger or smaller in max heap. If it is smaller, swap it. Okay, 7 will be top, 5 will be bottom. Okay, since it's a max heap, parent node should have the greater value than its children. That is the main concept. Okay, so 5 I have inserted, 7 is inserted. Next is 3. Okay, so since left is already full, I'll fill it. Check with the parent node whether it is greater or smaller. It is smaller, so don't have to change. Okay, next is 1. 7, 5, 3, where you insert 1, left as possible. 1. Next is 6. Okay, left as possible. Okay. Now, after inserting, check with its parent. 6 is greater than 5. So, swap these two. You don't have to do any kind of rotation, just swap. Normal swap. Okay. 6 will be here, 3 will be here, 1 and 5. Just swap. 6 and now the swapped 6 came here. Check with its parent 6 and 7. It is smaller, so don't need to do anything. It is max heap. Next is 9. So where you will insert 9. So if this is a tree, 7. Okay, so I'll move this little bit. So now 7, 6, 3. Okay, 1 and 5 is the tree. Okay, just draw. I have drawn the same thing here. Next node to be inserted is 9. Keep left as possible. Okay, already these two places are filled. Now left as possible. Okay, so next places, this is the position that I have to fill. I have filled. Check with its parent. Parent is 3. 9 is greater than 3. Since it's max heap, you should have maintain the property of max heap by keeping maximum element in the root node. Okay, so maximum element, so swap it. So how the tree looks like? Okay, uh, okay, fine. So swap it. So how the tree looks? 7, 6, 9. Okay, 1, 5, 3. Okay, now 9 is inserted. Check 9 with the 9 got its new position. Now check with its parent. What is its parent? 7. Is 7 is greater or smaller? It is smaller than 9. So to maintain the max heap property, swap this also. 9, 6, 7, 1, 5 and okay. So 9 is the largest element. It should reach the topmost position or it should be at the top of every other small nodes. Okay, so this is what max heap. Okay, next last element to be inserted is 10. Okay, so keep left as possible. So these in this level every place position. So keep remember that left as possible means you have to fill the level wise. Okay, or first the pre level should be filled, then only you should go to the new level. Okay, that is what your property of complete binary tree. Level wise filling, keep left as possible. Okay, so this level, so you know about levels, right? This is 0 level, this is first level, this is second level. Okay, okay, second level you had one portion, so I filled this node 10 here. Okay, check with its parent. Its parent is 7. So 7 is smaller. Since it's a max heap, parent node should be greater value. So swap this. So what happens? 9 will be here. 6 will be here. 10 comes here. 1, 5, 3 and 7. and again check with its parent. Okay, its parent is 9. So what you have to do? You have to just swap this two. Okay, swap these two. When I swap, 10 comes here and 9 comes here. This is the max heap. Okay, so it is max heap and it is complete binary tree where you have filled the tree in a such a way that level order filling you have done by keeping left as possible. From the left you have started and you have filled it level order wise. Okay, next then you it is max heap because every parent node is greater than its children. So 10 is greater than 6 and 9, 6 is greater than 1 and 5, 9 is greater than 3 and 7. So this is what max heap. Similarly, in mini heap means you have to create a tree in such a way that your minimum, the values will be minimum than its children. Okay, the parent node will be having minimum values than its children. Okay, so I'll just show you how to draw. Okay, so mini heap. Okay, so 5 I'll insert. Okay, so I'm talking about mini heap now. Okay, mini heap. I'll change the color. Fine. Okay, so mini heap. So 7 is the next node. I'll insert by keeping left as possible. Okay, so first level 0 is full. Now level 1. So first you have to fill the left node. 7 is full and check whether it is greater than the parent. Yes, sorry, lesser than the parent. No, it is greater, so it is fine. Next is 3. This is the next portion I have to fill. So 3, check with its parent. It is smaller than its parent. So in bin heap, parent should be lesser than its children. So swap it. This and this, I'll swap. Okay, so 3 comes here and 5 goes here. Okay, so lesser value than its children. Okay, next is 1. 1. So this level is full, level 0 is full. Now level 1 is full. Fine. Next is level 2. Okay, so level 1 you will have only 2 children. Okay, in level 3, level 2 you have 1, 2. Each node will have 2 children. So you can have these many children. Okay, at level 2. Okay, but start from the left. Okay, next is 1. Okay, now 1 is checked with its parent. Its parent is 7. Since it's a min heap, your parent should have the lesser value. So swap it. Okay, so 1 comes here and 7. Fine. So now 1 is compared with its parent. So parent should be the lesser value, right? So 1 comes here and 3 come here. Okay. Next, so 5 is full, 7, 3 is full, 9, 1 is full. Okay. Next is 6. So keep left as possible. It is not, so 6 is compared with its parent. It is, the parent is having lesser value. So leave it. Now 9. Okay, 9 is inserted in the next position by keeping left as possible. Okay, 9 is greater than 5. So don't have to change. Next is 10, just fill it. Okay, so 10 is compared with this children. Children is smaller value. Parent has the smaller value, so leave it. This is how you create the min heap. Okay, so min heap and max heap. Remember, it should be created by with the complete binary tree property. Okay, so this is how you will be doing this min heap and max heap. And one more thing, what you have to remember is, so till now we were seeing how to do this min heap and max heap. Okay, so I'll tell you some properties or representations of this binary heap tree. Okay, so or binary tree representation. So if your okay, so I'll take an example. C, E, F, and G are the nodes. Okay, for example. Okay, so we won't have this kind of structure, but in a memory, you'll have array kind of structure, right? Okay, this array only will be swapped here and there. Okay, you have this kind of structure, right? A, B, C, D, E, F, and G. Okay, 1, 2, 3, 4, 5, 6, 7. Okay, okay, so this tree I have represented in the form of array. So you won't have this picture in your memory. You will have this picture in your memory. But the data will be arranged in here and there. It will not be a continuous fashion. That is the matter. But this is how your data will be arranged in computer's memory. Even though it is a tree, it will be arranged in this way. Okay. So to if I is the node, okay, for example, for a node I, okay, for node I, to find this I's left child, you have to do this to find left child, okay. To find this I node's children or right child, you have to do this formula, okay. To find a parent, then you have to go for I by 2 floor value. Okay, I hope you remember this floor value and ceiling value. Okay, so I'll take a node and I'll tell you. Okay, so for example, I'm taking 4 as the node. Okay, so I is equal to 4 now. Okay, so 1, 2, 3, 4, 5, 6, 7. I is equal to 4 now. So I want to find this force or 4 means this. Okay, 4 I don't take because it doesn't have any. Okay, I'll take 3. Okay, fine. Okay, so I is equal to 3. Okay, by seeing we know F and G are the left and right chain, but computer doesn't know because it won't have this kind of representation. It will have this kind of representation. So if an array is given and if they are asking you to find its left and right child for binary trees or any kind of binary tree, okay, binary tree, okay, then you have to go use this formula in order to find it. So if I is equal to 3, it is left child will be 2 star I is equal to 2 star 3 is equal to at 6th position. What is 6th position? F is left child of, sorry, it's not 4, sorry. So for 3, 6 is its left child, okay. 2 star I plus 1, so which is 2 star 3 plus 1 is 6 plus 1 is equal to 7th question value is right child of 3. Okay, this left child and this is right child. So see here at 6th position F. Okay, so 6th position element is F and 7th position element is G. Okay, so in pictorial representation, F and G is the element left and right child of C. But in array representation, you have to use this formula to find which position is its left and are the left and right child is available. Okay. For example, if I want to find particular node's parent, for example, for node 6, I want to find the parent. Okay, 6th node's parent. Okay, so I want to find it. How to find? By using this formula, I by 2. So I is equal to 6. 6 by 2 is 3. So you have to, if here there is no, you didn't get any decimal value. So I'll just take it. Or else if the decimal values, if you got decimal values, then you have to use floor value. So 6th position, the element's parent is at 3rd position. Okay, what is it? C. So 6th position, the element is F. F's parent is C. That is at 3rd position. So likewise, by using the array index, by using this formula, you will get the array index, and through the index value, you can retrieve the data from the array that is stored in the array. Okay, so this is also an important concept in min and max heap. Not only in min and max heap, for any kind of binary trees, you can use this formula to find its left and right children. Okay, so the array, so how the array representation is filled? So in this fashion, okay, level wise, okay, from A, B, C, D, E, F, G. Okay, so likewise, you have to fill and you have to put the position. When you apply this formula, you can find its left and right children. Okay. Fine. So now there are two operations in binary, sorry, min heap and max heap. One is insertion and another is deletion. Another is deletion. So when you are inserting an element in min heap or max heap, your element should be inserted. Okay, in the left as possible. Okay, now I have created a tree, right? So in that 5 7 9, so 5 is created, then 7 as left as possible. Likewise, you have to create a new tree. And similar way, if you want to delete an element from the tree, you should choose only the root node or the largest node to delete the tree. Okay, so for example, I'll take an example and I'll help you to do how to perform insertion deletion by using min and min heap and max heap. Okay, I'll create a tree, then I'll tell you how to do this insertion. Okay, 35. Okay, so the elements in the tree are, okay, so 33, 35, 42, 90, sorry, okay, 90, 27, 44, 56, and 31. So insertion in leaf node and delete in root node. Okay, so please remember. So I'm going to create binaries, heap tree by using max heap. Okay, so if I teach you max heap, you can do it for min heap also. Okay, so I'll teach the max heap is a little bit complicated than min heap. So I'll start with max heap property. Okay, so first is max heap. Okay, so how to create insertion means creation and insertion is same, right? So 33. Let's start with 33. Okay, first I have inserted this node. Okay, next what I have to do is next element is 35. Okay, so I have created 33, now 35. So 35 and keep as left as possible. Okay, so I have created it. Okay, next is now you have to, since it's a max key, I have to check with its parent. Okay, so how the parent is checked? So this parent is 33. Max heap means you have parent should have the largest value. So what you have to do here, 35 is small, greater than 33. So swap it, just swap it. 33 and 35 comes here and 33 will be here. Next is 42. So keep left as possible. So next position is here. Okay. Now check with its parent. Okay. So 42, after inserting every node, check with its parent. If it is max heap, then parent should have the maximum value to swap. So swap. So here 42 is inserted. It is greater than its parent. So swap it. 42 comes here and 35 will be here. So now this is max heap and complete binary tree. Next is 19. Okay, so 19, check with its parent. The parent is greater, so leave it. Next is 27. Okay, so 27, check with its parent. It is greater, so leave it. Next is 44. Okay, so how to insert 44? So I have inserted 44 in the tree. Now check with its parent. Parent having the lesser value. So it is max heap. So parent should have the greater value. So I'll swap it. 44 here and 35 here. Now again, check the swapped node with its parent. So 44 and 42. So swap it. So since it's max heap, parent should be at the topmost position, 44 and 42. Okay, so now it is max heap and complete binary tree. Next is 26. So 26 here. Check with its parent. It is smaller, so leave it. Next is 31. So next position here. 31 is greater than its parent, so swap it. 19 and 31. Sorry. Sorry, 31 comes here and 19 will be here. Check with its parent. So 31's parent is 33. So it is greater. So leave it. So this is your max heap. So now we have created and inserted elements in max heap. The same thing I'll teach you with the array representation. There are 1, 2, 3, 4, 5, 6, 7, 8. 8 elements. Okay. So please listen. 1, 2. My array index starts with 1. We can have any kind of value start. So 8. Okay, so these are the array. Okay, so first, what is it? 44 was there, is here, and 33, 42, 31, 27, 35, 26, and 19. Okay, so I told you, I hope you remember, I is a node, then 2 star I will be left child. Okay, 2 star I plus 1 will be right child. Okay. I by 2 will be parent. Okay. So fine. So I is equal to 44. Okay. For example, if okay. So okay. Initially you won't have these elements inserted because now only you are going to create a tree. Okay. So now you are going to create a tree by inserting the nodes in its position. So the 8 positions. So there are 8 nodes. So 8 position is created. So first 33 will be inserted in the tree. Okay. So computer will insert here. Okay. Next element is 35. Okay. So now I is equal to 1. Okay. So we have to check the left child whether it is greater or smaller. Okay. Okay. Next, so to check that, you will go for 2 star I concept. So I's left child will be found by 2 star I. So 2 star 1 is equal to 2. So 33. So I is 1 and 2 is the two, second question is the right node, right? So check these two nodes. Okay. So check whether it is greater or smaller. If it is greater, swap it or else do not swap it. So 33 is compared to 35. It is greater. So swap it. Okay. So 35 comes here and 33 will be here. Okay. I hope you are getting what I'm trying to do. So how I'm teaching how the computer will be doing this swapping. It will not have this three kind of structure. It will have this array kind of structure. It has to find its left and right child by its own and it has to do the swapping, appropriate for swapping. Okay. Next is two. So third next element is so 33 is full, 35 is full. Next is 42. Okay. So or else I can go in reverse way. So for 42, I have to check with its parent. So 42 is at third position. Okay. So third position, right? So I is equal to 3 now. So to find its parent, I have to use this I by 2 formula. 3 by 2 is 1 point something. So you have to take the floor value. So 1 is its parent. So 42, that is the third position element's parent is at 1. So check with its parent. Okay. 32 is compared with 35 and you find that since it's a maxi, parent should be having the greater value than its children. So 42 is greater than its parent. So swap it. Okay, 42, 35. So 42 comes here and 35 will be here. So now your maxi properties satisfy. Similarly, to insert next node. Okay, so don't get confusion. I'm just teaching you how to do in computer point of view. Next element to be inserted is 19. Okay, so 19 is at fourth position. So I is equal to 4. So 4 by 2 is 2. So second position element is its parent. So 39 and 7 is compared. So this is parent and this is child. Child is compared with its parent. If it is greater value, swap it. If child has the greater value than its parent, swap it. If not, leave it. So it is okay because child is having lesser value. So don't swap. Okay. Next element to be inserted is 27. Put it here. Okay. 27 is at fifth node. So I is equal to 5. To find its parent, 5 by 2. So 2 point something. Take only the floor value. So this element's parent is at, that is, this element parent is at second location. Check with its parent. Compare with its parent. Since it's a max heap, the parent should have the maximum value. So it is parent is already having the max value. Don't swap. Similarly, next element to be inserted is 44. 44 is that I is equal to 6 now. 6 by 2 is 3. So this element's parent is this element. So check with its, so here 44 is greater, that is child is greater than its parent. So swap it. 44, 35. Okay, so here comes the 44 and 35. Don't stop here. Compare again. So the swapped element is at this position. Okay. So I is equal to 3. So now to find its parent, 3 by 2 is 1. Okay. Take floor value. So this node's parent is as at first position. Okay. 44 is greater than 42. So swap it. So 44 comes here and 42 will be here. Fine. Likewise, you swap. Next is 26. 26 is at node 7. So I is equal to 7. 7 by 2 is 3 point something. So third node is its parent. So it is smaller. So third node and seventh node. So it is smaller than, the child is smaller than its parent. Don't swap. Then is 31. Okay. 31 is inserted. So now I is equal to 8. 8 by 2 is 4. So this and this is parent and child. Okay, so this is child and this is parent. So child should not be greater than its parent since it's a max heap. So swap it. Okay, so 31 will be there. So okay, so now parent came here. Okay, so sorry, this is child of what node? So I is equal to 4 now. So 4 is 30. For 31, we are checking with its parent. Okay, 31. So 4 by 2 gives you 2. So this is your child of node 2. Okay, so 33 and 31 is compared. They are in the normal position, so don't swap. So likewise, only the computer will be doing its insertion operation. Okay, it will not have this kind of tree structure. Okay, so please remember this way to insert a node in min heap or max heap or any kind of binary search tree. Okay, I don't want to confuse you. Just remember what is min heap, max heap. Okay, so now we have inserted the node. Okay, now we have to delete the node. How to delete it? Okay, deletion will always happens in root. Okay, so from the root you have to delete. Okay, so first element you can delete only is 44. Okay, so if I want to delete the element, okay, so okay, for example, I'll take this also. Okay, so 1, 2, 3, 4, 5, 6, 7, and 8. Okay, so first I'll show this way first, then I'll use this array way to explain you. Okay, so why I'm doing this array way? Because it will give you another topic. So that only I'm including this also. So please remember. Okay. Fine. So I'll teach you both representation as well as array representation to this diagrammatic representation and array representation to delete a node. First, I'll do this. Okay. So since it's max heap, I can delete only the, even it is max or min heap, I can delete only the root node in heap tree. Okay. So this is heap 44 is the first node to be deleted. So if I delete this, what happened? The lowest element in the last will be replaced with it. Okay, so I deleted 44. So 44 was here, and I have inserted the last element or the lowest element with it. Okay, so 19 will reach its position. Okay, now check the max heap property. Okay, so the first element deleted is delete 44. Okay, so next, so now check the max heap property. Max heap property is you should have the parent node as the greater elements. The greater element should be in the parent node since 19 is smaller than its children. Okay, so check among these two children which is greater. 42 is greater. So swap with it. Okay, so 42 comes here, 19 will be here. Okay, so now at root node, it is satisfied. Now check again with its children. This 19 is check. This is the swap part, right? So check 19 with its children. It should have the greater value, right? So among these two nodes, which is greater, 35 is greater. Swap with it. 35 comes here and 19 is here. So now it is max heap. After deleting 44, this is your max heap. Next, what is the next element to be deleted? That is 42. Delete 42. Okay, so delete 42. So after deleting 42, what element will reach this position? The smallest element. What is the smallest element? So take, this is the not a smallest element. Next, last leaf node. Okay, the last leaf node should be taken and replaced here. So this is the last leaf node. So replace here. Okay, while filling you started from left side, but while deleting you have to do it in reverse way. Okay, so filling was happened this way, right? From root node you fill left to right, but deleting from left, that is reverse way. Okay, so filling this way now. Okay, so right, I'll draw again. So filling you had started with this side, then this way. All right, but deleting you have to do this way. Okay, so this deleted first, then this deleted. Okay, so 90, so now 26 replaced with the top after deleting 44. Next position element in the last is 26, so that I have replaced. Okay, I have to check the max heap property. After this max heap property, the parent should have the largest value, right? So the parent node, so check with its children, 33 and 35. Okay, so this, it's not max heap, so replace it with the biggest children. Okay, so that is 35 is the biggest, so swap it, and 26. Okay, now check with this children, it has only one child and it is greater, so it is max heap. Okay, next the element to be deleted is 35, because only large elements can be deleted and the largest element will be always at the top position. Okay, or the root position. So 35, delete 35. After deleting 35, what should be replaced? It should be replaced with the next node, that is 19. 19. I have deleted 35. So check with its children. So children is having greater value. Among the two children, put the greater value. Swap with this greater value. So 33 will be here. 19 will be here. Okay. So check with its children. So 33 and 27 are greater than 19. Among these two children, choose the greater value. So 19 will be coming here and 31 will go up. Okay. So now it is max heap and we have deleted 35. Next, what element to be deleted? You have to delete 33. So after deleting 33, what happens? The last node, that is 27, will reach its position, this position. Okay. So I'll delete this also. 27 is compared with this children. 31 is having the higher value. So swap. 31, 27. Check with the children, it is having. So this is min heap, max heap. So 5. Okay. So next to 5, fifth element to be deleted is delete 31. Okay. So to delete 31, I have deleted it and replace it with the next child, that is 19. Okay. 19 is greater since it's a max heap. Root or the parent node should have the greater value. Among its children, swap with its greater node. Okay. So 27 comes here and 19 will go down. Okay. So next element to be deleted is delete 27. So delete this and swap with its the least child, or not least child, the next child. You have to go this way only. 26 is greater. Next, it is max heap. So now delete 26 and swap with its greater last child. 19 will come here. Again, at the end, you delete 19. Okay, so this is how you can delete a node from a max heap or min heap tree. Okay, delete the root node only. Similarly, in min heap, you will have in some other way, right? For example, if it is min heap, what are the elements? So I'm just using the same elements. So what is min heap property? 33. So smaller values will have the greater position. 19 will be here. So I'll do this properly. Okay, 33 first and 35. It is min heap, so don't change. Next is 42. Don't change because it is min heap property. Then it is 19. It is smaller than its parent, so swap. So 33 comes here, 19. Again swap. Okay, 19 and this is 35. Okay, next is 27. Put here. It is smaller than its parent, so swap. 27. Here it is 35. Okay. So don't think that I'm doing faster. I'm just using min heap to put the values. Okay. Next is 44. It is okay. Then it is 26. Swap 42 and 26. 26 and 42. It is not smaller than its parent, so don't change. Then it is 31. 31, its left child is left and right. Compare with its parent. Parent is having the greater value, so swap. Because it is min heap. Okay, so since it's a min heap, we are using greater value, smaller value as it in the root node. Okay, this is min heap. Okay, for deleting, you have to start with the root node only, and you can in min heap you can delete only the root node element. So in order to delete, you will be deleting first. 19 will be deleted first in reverse order. 19 will be deleted first. and replace with its last child, that is 33. Okay, again you have to validate the property of min heap, swap it with its children, least children. Okay, so 33 is swapped here. Since 19 is the first node to be deleted, delete 19. Okay, then I swap, so 33 will be the last child, so that will be replaced here, and you compare with its children. If it is having lesser value, swap it with its least child. Okay, so 26 comes here and 33 will go down. Okay, 33 will come here. So likewise, you have to do this min heap and max heap accordingly. Okay, so now this this form of comparing and changing. Okay, now what you did, you compared with every element and you have satisfied the property of either min heap or max heap by swapping the element one by one, and this is called as heapify. To maintain the property of heap tree, you have swapped the elements one by one and you have managed to settle the elements in such a way that your max heap property or min heap property is not violated, and this method is called as heapify. You have swapped and did some work, right? That is what called as heapify. Okay, the same thing. Okay, so now I'll find, so I'll teach you what is heap sort is. Okay, so the last concept is heap sort. I have deleted is that. So 42. Okay, so first, fine. So I'll do max heap again because I want to teach you how to do the heap sort. Okay, so or else I'll take one new thing. Okay, so I'll take some data like 5 random data, smaller data, 1. Okay, so these are the elements. Now I'll create max heap. Okay, uh, okay. First, okay, by using this. Okay, so 1, 2, 3, 4, 5. I 2 star I 2 star I plus 1 and I by 2. Okay. First I'll insert 5. Next element is 7. So 7 is at position 2. Okay. 7. Suppose I is equal to 2 now. So to find its parent, 2 by 2 is 1. 1 was its parent. So computer don't know this kind of thing. So it uses formula. So 1 is the left is its parent. So if the parent is, it is max heap, so the parent should be having greater value. So here I is child, 7 is child, and 5 is parent. So swap it. Okay. Now it is okay. Next is 1. Okay, so 1 is at third position, I is equal to 3. So to find its left child, 3 by 2 is 1 point something. You have to take the floor value. So 3 is parent is this one, 7. That is third position element, parent is first position element. So 1 is 1 and 7 is compared. Since the max heap, parent should have the greater value. So it is already there. Okay, next element to be inserted is 3. Again, I is equal to 3 now. That is 4. Index is 4. Okay, so 4 by 2 is 2. So this fourth position element parent is at index 2. Compare with its parent. So the parent is having a greater value. Don't do anything. Next is 2. Similarly, I is equal to 5 now. 5 by 2 is 2 point something. Take the floor value 2. So this is parent, this is child. Okay, compare with its parent. If it is greater, leave it. If it is smaller, swap it because it's max heap. So now the elements are inserted inside the max heap. Okay, so now we'll do deletion operation. Okay, so what is the how to do deletion operation? The same way, the first always this is the first element and the root node. Okay, so always this element will be deleted. The element's position inside this first element, first column or first box will be deleted because this is the position of root node. So first element to be deleted is 7. So I have deleted 7. So what will be coming inside next? Okay, this 2 will be coming inside. Okay, so now here 2 I have deleted. Okay, because 2 is replace to the first position. Okay, so the element I have deleted. Okay, so here, so what happens here is, now you have to compare its left and right child. Okay, so because 2 is the topmost element, now you have to compare with its left and right child. What is left child? Okay, so I is equal to 1 now. So 2 is at first position, so I is equal to 1. Its left child will be 2 star I, that is 2. So what is second position element? That is 5 here, and 2 star I plus 1 is equal to 3. What is third position element? That is 1. So this element, these are, since it's a max heap, root element should have the, or parent should have the highest value, greatest value. So swap with its pair children. Okay, so 5 is greater, so I have to swap it. So how? So here I'll just swap like that, 2 and 5. Okay, so now 5 here, 2 here. Okay, so what happens to this places, since this is 2's position, this 2 was initially here, so I'm just going to fill the deleted element one by one. I'll just fill this. Okay, what element was deleted? 7 was deleted, so I'm putting 7 in the empty space over here. Okay, next you have to do, so don't compare this. Okay, because this is the position of the deleted element. Okay, so now 7 I have put inside. Next is you have to do the comparison for these 4 elements only. I is equal to 1 to n minus 1. Okay, so now you have to find the left and right. Now I have to delete the next element, is this element will be deleted, and you have to replace it with 3. The next smallest element is 3. Okay, so the next element here is 3. Okay, so now I'll delete this element. Okay, so because 3 came here. Okay, so now, okay, so now what happened here is 3 came to the first position. What will be the left and right child? Same thing. So 3, I is equal to 1 here. So I is equal to 2 star I. So left will be 2 star I. So that is 3. So third position, second 2 star I is 2 star I is equal to 2 star 1, which is 2. So second position element is 2. He will come here in left side. And 2 star 1 plus 2, 1 is 3. Okay, so right child will be 2 star 1 plus 1 is equal to 3. Okay, so third position element is 1. Okay, since it's max heap, it is already in max heap property. Okay, so don't do anything. Okay, you have deleted it properly. Okay, so what happens here is I'll put the deleted element inside the empty space. Okay, so now the next comparison happens for these 3 elements only. Okay, so the next, so now, okay, so I'll delete, I erase this also. So next element to be deleted is set node I is equal to 1 is deleted. Okay, so I'll delete this. Okay, and I'll replace with the smallest element here. Okay, that is the next node to be, I'll replace this position. Okay, so I'll put this deleted element over here. Okay, so compare with its children. Okay, that is, if I delete 3 and I replace with this element. Okay, here. Okay, think in this way. So what happens? You have to check whether it is max heap. It is not max heap, so swap it. 2 1 1 is swap. So how you will do here? I is 1. Its left child will be at 2 star I, that is at second position. So 1 is compared with 2. It is having the greater value. So swap it. 2 will be here, 1 will be here. So now I have stored the deleted element in the empty space. Now, next what you have to do, you can delete only the root element. So 2 is deleted. If 2 is deleted, what will be here? 1 will come here, right? So likewise, I'll do. Okay, so 1, since only one element is there, I'll put this 2 here. Okay, after deleting 1, 1 also will come here. Okay, so when you are deleting the element and putting the element one by one in the empty space, what you got? You got a sorted order. If it is a max heap and you're deleting the element one by one and you're arranging the element in an array, you'll get ascending order sorting. Okay. Similarly, if it is min heap and you're deleting the element and you're putting the element one by one in an array, then you'll have descending order sorting. Okay, so please remember these two things. Okay, so when you are doing max heap and you're deleting in your max heap, when you're deleting an element, and if you're putting the deleted element one by one in a array, then you'll have ascending order sorting. Similar way, when you are in min heap and you're deleting an element, deleting the element one by one, starting from the root node, and you are arranging the deleted element in an array, then you'll get descending order sorting. See here, 1, 2, 3, 5, 7 is the sorted list. Okay, so because of this heap tree can also be used for sorting, and that sort is called as heap sort. Okay, so we saw what is heap tree. That is, it has complete binary tree plus max heap or min heap, right? Then we saw what is how to insert and delete. Okay. And we saw what is heapify, and we also saw what is heap sort. Okay, so this is the entire concept of heap sort. Okay, so now only one more thing is left, that is priority queue. It is just a normal thing. Okay, so what is priority queue? It's a priority based queue data structure. Like, you have the same front and rear everything. While you are inserting, and each element has its own priority. While inserting and deleting, you use this priority option to insert an element and delete an element. So it's an abstract data type that behaves similar to the normal queue, except that each element has some priority value associated with it. Either you can go for ascending order priority or descending order priority. Okay, so if these are the elements in priority queue, if it is ascending order sorting, okay, ascending is the priority, then one will be having the highest priority while inserting. If these elements given in the hand, and if ascending is the, for example, I'll tell you. Okay, just one moment. Okay, so okay, these are the elements in the queue. Okay, these are the data given in a hand, and if they are asking you to insert in a queue data structure by using priority basis, and the priority is ascending order. So which element will have the, so is the ascending order now? The smallest element will have the highest priority. So the first element will be inserted as 1. The second element, second will be 2 and 5, then 7 and 9. So it will not, if normal queue, 9 will be inserted and 7 will be inserted first. But if it is a priority queue and it is given, the priority is given as ascending or descending, then the according to that priority, the queue elements will be inserted. If it is a descending order priority, 9 will be inserted first, followed by 7, 5, 2, and 1. So similarly, while deleting also, priority is associated and deleting will comes the same way. Okay, so this is how what is priority queues. Okay, so you have priority associated with the elements, and you'll be inserting and deleting accordingly. Okay, so this is what heap sort and heap tree and priority queues is about. Okay, thank you.